These are 5 fascinating mysteries that have captivated the brightest minds for decades, pushing the boundaries of our understanding of reality. 1. Dark matter, the invisible force that seems to hold galaxies together yet remains elusive. What is its true nature, and how does it shape our universe?
For all the progress that we have made in understanding the universe, we are still in the dark regarding some 95% of what is out there.
2. Dark energy, the enigmatic energy that drives the universe's accelerated expansion. What secrets does it hold about the fate of everything we know?
The fact that dark energy pervades the whole universe and is slowly changing, that should immediately set off alarm bells, because particle...
3. Singularity, the heart of black holes, where the laws of physics, as we know them, break down. What happens beyond this point of infinite density?
A singularity in physics, the word really refers to any region of space and time where the conditions are so extreme that our mathematics breaks down. And
4. Time, an ever-flowing river that we struggle to understand. Is time a linear progression, or could it be more complex than we perceive?
Time makes us all a prisoner of the present, forever transitioning from our own past into an unknown future. And that's particularly disturbing to me, because we can move back and forth in any other coordinate. You know, up and down, left and right, forward and back, but we're stuck in time.
5. Space. The fabric of space is not a tangible entity that can be touched or seen. However, its effects are undeniably real and can be observed in various phenomena.
Well, you can't understand anything about the world unless you understand space, because that's the world. The world's space with stuff in it.
We're not usually very conscious of space. But then again, I tell people fish are probably not conscious of water either. They're in it all the time.
Space is not really nothing. It actually has a lot going on inside.
Join us on an adventure into the unknown, where our everyday intuition and the laws of physics seem to unravel, pushing the boundaries of our understanding of reality.
Actually, we shouldn't call it anything. We should call it Fred. Something that has no meaning, because we don't know what it is to call it. But it is the longest standing unsolved problem in modern astrophysics.
Dark matter, an elusive and enigmatic substance that constitutes 27% of the universe's total mass energy. It is the scaffolding for cosmic structures. It helps galaxies form and cluster together, creating the universe's large-scale structures. Unlike ordinary matter, it does not interact with electromagnetic forces, rendering it invisible to our current instruments. This unique property, which prevents it from absorbing, reflecting, or emitting light, challenges our traditional means of observation, making it one of the most compelling mysteries of the cosmos. Scientists have developed ingenious indirect techniques to identify the presence of dark matter. A primary method involves gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. Gravitational lensing occurs when the powerful gravitational fields of massive objects, such as dark matter clusters, warp the light from distant galaxies. This bending of light results in the distorted shapes of galaxies and even creates multiple images of the same astronomical object, providing us with a fascinating peek into the mysterious world of dark matter. Another important method for detecting dark matter involves studying the motion of galaxies, particularly spiral galaxies. When astronomers closely examine the speeds at which stars orbit the outer regions of these galaxies, they often find that these speeds are much higher than expected based solely on the visible mass. This surprising discrepancy suggests the presence of an additional, unseen mass of dark matter exerting its gravitational influence on the stars. Through indirect observations, researchers are gradually piecing together the mystery of dark matter. Their goal is to uncover its properties, map out its distribution, and grasp its role in the formation and evolution of the universe. Weakly interacting massive particles, WIMPS, and AXIONS are leading theoretical candidates in the search for dark matter. WIMPS are predicted to be heavy particles that interact through the weak nuclear force and gravity, making them exceedingly difficult to detect. Their properties suggest that they could have formed in the early universe during a phase of rapid expansion. Scientists are actively searching for WIMPs through various experiments that aim to observe their interactions with ordinary matter. On the other hand, AXIONS are hypothetical particles that arise from specific extensions of the standard model of particle physics, particularly in efforts to solve the strong CP problem. These ultralight particles are characterized by very weak interactions, making them elusive and challenging to detect. The search for AXIONS often involves observing phenomena predicted by their presence, such as conversions in strong magnetic fields. WIMPs and AXIONS play a crucial role in astrophysics and particle physics, as scientists strive to unravel the mysteries of dark matter and its influence on the universe. Despite considerable research efforts, these elusive particles have yet to be directly observed due to their complex nature and the difficulties involved in detecting them. On the other hand, modified Newtonian dynamics, MOND, offers an alternative perspective by suggesting that the laws of gravity may operate differently under conditions of very weak gravitational fields, such as those found at the outer edges of galaxies. This theory has shown promise in explaining several phenomena related to galaxy dynamics, including the rotation speeds of stars. However, MOND encounters challenges when it comes to accounting for relativistic effects, such as gravitational lensing, the bending of light by massive objects, and the dynamics of gravitational waves. Thus, while MOND provides some intriguing insights, it fails to address all the complexities of gravitational interactions in the universe.
Equipment. The surprise then is not that there is invisible stuff out there, stuff that for historical reasons we don't call invisible, but rather we call dark. Rather, the surprise is how much dark stuff
Dark matter
there
is estimated to account for about 27% of the universe's total mass energy content. To better understand this, let's examine the universe's overall composition, which can be roughly broken down as follows: 68% dark energy, 27% dark matter, 5% ordinary visible matter. This means that there is approximately 5 times more dark matter than ordinary matter in the universe. This significant difference is not just an interesting statistic. It highlights a major gap in our understanding of the cosmos and the fundamental forces that govern it. Dark energy is a fundamental component of the universe, intricately linked to its expansion and serving as the catalyst for its accelerating growth. Current estimates suggest that it accounts for roughly 68% of the cosmic makeup, highlighting its significant yet mysterious presence. In contrast to dark matter, which has been the focus of extensive research and scrutiny, dark energy remains poorly understood and largely theoretical, shrouded in enigma and inviting further exploration into its true essence. One theory suggests that dark energy is linked to the cosmological constant, a concept introduced by Albert Einstein in 1917. He added this constant to his equations of general relativity to support his vision of a static, unchanging universe. Essentially, the cosmological constant serves as a repulsive force that counterbalances gravity, helping to stabilize the universe and prevent it from collapsing. However, in the 1920s, when Edwin Hubble discovered that the universe was actually expanding, Einstein considered the cosmological constant his biggest blunder and removed it from his equations. Fast forward to the late 20th century, astronomers examining distant supernovae made a groundbreaking discovery. Not only is the universe expanding, but this expansion is also accelerating. This unexpected revelation led scientists to rethink the cosmological constant as a possible explanation, tying it to the enigmatic concept of dark energy. In a fascinating twist, Einstein's original idea had come full circle. However, a significant issue arises concerning the cosmological constant. The problem stems from the immense gap between the observed value of the cosmological constant or vacuum energy and the figure predicted by quantum field theory. This discrepancy is staggering, reaching an astonishing 10 to the power of 120 times higher than expected, which is simply mind-boggling. This conundrum is commonly referred to as the vacuum catastrophe.
In physics, it's never been wrong. It's our best understanding going. When you do that calculation, the answer you get does not match reality. The answer you get is off by a factor of 10 to the 20th power. That's a 1 followed by 120 zeros. We put forth our best theory to our biggest problem, and it gets us nowhere. In fact, it is the biggest mismatch between theory and observation that there ever was in the history of science.
The cosmological constant is one explanation for dark energy, which is believed to be responsible for the universe's accelerated expansion. However, due to several challenges related to this concept, some physicists have proposed alternative theories for dark energy. One prominent alternative is quintessence.
Since I like to talk to people in different areas, I was sort of more familiar than average with what a respectable working particle physicist would think about these things. And what I immediately thought was, you guys are throwing around these theories. These theories are wildly unnatural. They're super finely tuned. Like any particle physicist would just be embarrassed to be talking about this. But rather than just scoffing at them, I sat down and asked myself, okay, is there a respectable version? Is there a way to keep the particle physicists happy, but also make the universe accelerate? And I realized that there is some very specific set of models that is relatively natural. And guess what? You can make a new experimental prediction on the basis of those. And so I did that. People were very...
Quintessence is a fascinating theoretical concept that offers a different approach to understanding dark energy. Unlike the cosmological constant, which is defined as a fixed energy density permeating space uniformly, quintessence describes a form of dynamic and variable energy. This means that the properties of quintessence can change over time and across different regions of space. In quintessence models, the behavior of dark energy is described by the evolution of a scalar field, which is a fundamental aspect of these theories. This scalar field is not a constant. Rather, its energy density changes over time in response to various physical processes and interactions within the universe. The potential energy associated with this scalar field can vary significantly depending on its position and the dynamics of the surrounding environment. This variability means that quintessence can accommodate different scenarios and cosmological observations. As the scalar field evolves, it can influence the rate of cosmic expansion, providing a more dynamic framework that reflects the actual conditions of the universe. This nuanced approach allows quintessence to incorporate features like the possibility of future changes in dark energy density, potentially leading to different outcomes for the universe's fate compared to simpler models. Overall, quintessence offers a compelling way to explore and understand the underlying mechanisms of dark energy and its role in the cosmos. While models like quintessence struggle to explain dark energy, some groundbreaking theories suggest that dark energy may be an illusion and may not actually exist. The Timescape model offers an intriguing alternative to the standard cosmological framework, challenging the traditional view of the universe's expansion. instead of attributing the accelerating expansion to dark energy. This model suggests that local variations in gravitational fields influence the flow of time. In regions characterized by strong gravitational fields, such as galaxy clusters, time moves more slowly, while in the vast emptiness of cosmic voids, it speeds up. According to the Timescape model, a clock situated in the Milky Way galaxy would tick approximately 35% slower than a clock placed in these expansive voids. This time discrepancy implies that billions of additional years would elapse in these less dense regions. Consequently, this scenario creates a perception of significant space expansion, giving the illusion that the universe is accelerating, especially as these vast, empty voids begin to take over the cosmos. Dark energy remains a puzzling and elusive concept in modern astrophysics. While intriguing models such as Quintessence and Timescape offer compelling insights, they have yet to achieve widespread acceptance, leaving the nature of dark energy shrouded in uncertainty. Over the past few decades, researchers have put a significant amount of effort into understanding the complex nature of dark matter and dark energy. Despite the extensive work done, our grasp of these mysterious components of the universe is still far from complete. This is especially remarkable given that dark matter and dark energy are thought to account for roughly 95% of the total mass energy content of the cosmos.
So, here's what you do. You take the energy contained in what we call dark energy, and it's 70% of all that drives the universe. Include with that percentage the dark matter, and we are driven to the humble, mind-blowing conclusion that 96% of all that is the universe is not anything we even remotely understand. 96%. And that all of our laws of physics, everything we know, love, interact with, and understand, or even can predict anything about the future, that falls into the 4% that remains.
A singularity in physics, the word really refers to any region of space and time where the conditions are so extreme that our mathematics breaks down and prevents us from gaining, at least as of today, a complete analytic understanding of what's going on. So the two primary examples are the center of a black hole, where the powerful gravitational pull warps space and time so dramatically that even Einstein's mathematics breaks down at the center of a black hole, and similarly at the Big Bang, the entire universe.
Imagine embarking on an adventure into one of the universe's most mysterious phenomena, a black hole. As you approach its event horizon, the boundary beyond which nothing can escape, you notice how the light around you bends and warps, creating an awe-inspiring yet eerie glow. This stunning effect occurs because the immense gravitational pull distorts light in ways you have never experienced before. As you draw closer, the gravitational force becomes so powerful that time appears to slow down in relation to the rest of the universe. To an observer outside, it would seem as though you are frozen in time, teetering at the edge of a black hole. Once you cross the event horizon, there is no turning back. This is where things take a truly surreal turn. The gravitational forces stretch your body lengthwise while compressing it from the sides, a phenomenon often referred to as spaghettification. While the term may sound grim, it aptly describes the extraordinary tidal forces at play. As you descend further, you get closer to the singularity, the very core of the black hole. In this strange realm, time and space swap roles. Finally, you reach the singularity, where density reaches infinity and the laws of physics, as we know them, break down.
To the center of a black hole, you get black holes from Einstein. Center of black hole, there's a singularity. all the theories say the matter occupies zero volume, thereby having infinite density. And that's kind of weird. What? No, you can't have infinite. No. That's a limit of Einstein's theory. That's where it breaks down. Some have joked that's where God divides by zero. Remember in math class, you can't divide by zero.
Right.
It's not defined or not allowed. So in Einstein's equations, we're dividing by zero at the singularity. So we all know that as brilliant as Einstein was, and as successful as his general theory of relativity has been, it has limits. And one limit is the center of a black hole, and another limit is the very birth of the universe itself. Getting back to your question, the Big Bang. So,
The Big Bang singularity refers to the initial state of the universe at the very beginning of its expansion. According to the Big Bang theory, the universe started from an extremely hot, dense point approximately 13.8 billion years ago. This point, often described as a singularity, had infinitely high temperature and density, and it represents a moment where the known laws of physics break down. Here are some key points about the Big Bang singularity. 1. Infinite density. At the singularity, the universe's density was infinite. This means all the matter and energy in the universe were compressed into an infinitesimally small point. 2. Planck epoch. The Big Bang singularity marks the beginning of the Planck epoch, the earliest period in the universe's history, lasting from time 0 to 10 to the power of negative 43 seconds, the Planck time. During this time, quantum gravitational effects dominated, and our current theories of physics cannot describe the conditions. 3. Breakdown of general relativity. Just like with black hole singularities, the Big Bang singularity represents a breakdown of general relativity, indicating the need for a quantum theory of gravity. 4. Cosmic inflation. After the initial singularity, the universe underwent a rapid expansion known as cosmic inflation. This period of exponential growth smoothed out any irregularities and led to the formation of the large-scale structure of the universe. The nature of the Big Bang singularity raises many unresolved questions. For example, what caused the initial expansion? What was there before the Big Bang? These questions remain open and are the subject of ongoing research. So what occurs at the singularity? Does the very fabric of space and time start to unravel and ultimately come to an end, as predicted by general relativity? Or could the development of a new theory of quantum gravity offer us a deeper insight, pushing the boundaries of space and time into an entirely different dimension of reality?
I also think of time as this prison. Time makes us all a prisoner of the present, forever transitioning from our own past into an unknown future. And that's particularly disturbing to me because we can move back and forth in any other coordinate. Up and down, left and right, forward and back, but we're stuck in time. We can't move forward or backwards in time arbitrarily.
Time is a fascinating and complex concept that has intrigued philosophers and scientists for centuries. In simple terms, time refers to the ongoing sequence of events that occur in an irreversible order, moving from the past through the present and into the future. From a physical perspective, time is viewed as a dimension. When combined with the three dimensions of space, we create the concept of four-dimensional spacetime. Most of us have a basic understanding of four-dimensional spacetime. For example, consider having an appointment at 1020 Main Street, 6th floor, at 2:30 p.m. By integrating the dimension of time with the three dimensions of space, we define a four-dimensional coordinate or an event in space and time. We called this when and where. But what if your when is different from my when? Albert Einstein's theory of general relativity transformed our understanding of time by demonstrating that it is not a fixed quantity, but rather a relative concept. A key takeaway from general relativity is that time is relative, which means our perception of time isn't constant. It varies depending on the observer's situation. Several factors can influence this variation, including the observer's speed and the strength of the gravitational field they find themselves in. As a result, time can pass differently for different observers based on their relative movements and the gravitational forces acting upon them. This fascinating occurrence is referred to as time dilation. Consider a scenario involving a pair of identical twin sisters. If one of them were to embark on a space journey at a speed close to that of light, according to the theory of relativity, time would pass more slowly for the sister on the spacecraft than it would for her sister on Earth. As a result, when the space-traveling sister returns to Earth, she will be younger than her twin, who remained on Earth. This phenomenon is a consequence of time dilation, where the faster an object moves through space, the slower time passes for that object compared to an observer at rest. According to general relativity, time dilation becomes significant as an object approaches the speed of light. For a photon, which moves exactly at the speed of light, the passage of time in its own frame of reference is essentially non-existent. This means that from the perspective of a photon, no time passes between its emission and absorption, regardless of the distance it travels. The concept of a block universe, or block time, is connected to general relativity. In the block universe view, time is treated as a dimension similar to space, meaning that past, present, and future events all coexist in a four-dimensional space-time continuum. This model contrasts with our everyday experience of time flowing from the past to the future. Here's how general relativity leads to the idea of a block universe. General relativity describes the universe as a four-dimensional continuum where time is woven together with the three spatial dimensions. This fabric of space-time is influenced by mass and energy, curving in response to their presence. In the block universe, there's no objective present moment. Instead, all points in time are equally real, much like different points in space. This view is compatible with the theory of relativity, which shows that the distinction between past, present, and future is relative and depends on the observer's frame of reference. The block universe is a captivating concept that questions our intuitive understanding of time. It raises inquiries about causality and our perception of reality, and whether time truly exists or is merely an illusion. Quantum mechanics and general relativity offer fundamentally different perspectives on time. General relativity views time as flexible and dependent on the observer, while quantum mechanics considers it a universal and fixed entity. In the realm of quantum mechanics, it is proposed that at the subatomic level, the fundamental laws of physics exhibit symmetry even when the direction of time is reversed. Experiments confirm this symmetry for electromagnetism, gravity, and the strong nuclear force, although the weak nuclear force shows a slight deviation. Essentially, there is no preferred direction of time at the subatomic level, and the laws of physics remain unchanged whether time moves forward or backward. This concept challenges our everyday understanding of time and raises intriguing questions about the nature of the universe at its most fundamental level. Have you ever found yourself staring at a tangle of electrical cords and cables, wondering how they became so knotted? It might seem like they just magically went from being neatly organized to a chaotic mess at your feet, but deep down, you know that there's no magic involved. You understand that the wires gradually became tangled over time due to subtle movements. You also realize that without making a conscious effort, the tangled mess won't just magically sort itself out. It will only continue to become more disorganized as time goes on. This is because the second law of thermodynamics, or entropy, states that everything in the universe eventually moves from order to disorder. Entropy is a unique concept in the physical sciences as it is associated with a specific time direction, often referred to as an arrow of time. According to the second law of thermodynamics, as time progresses, the entropy of an isolated system can only increase and not decrease. For many physicists, this is tangible evidence that time exists and has a single direction. In theoretical physics, the clash between general relativity and quantum mechanics raises questions about the true nature of time and its singular direction. This captivating conflict delves into whether time is a distinct phenomenon or an emergent property of a deeper underlying reality. In the realm of philosophy, time is viewed as more abstract and subjective than in the field of physics. Philosophers engage in deep reflection on the essence of time, pondering whether it exists independently of human perception or is simply a mental construct. They grapple with intriguing questions such as, what does it mean to live in the present? How does the past shape our current experiences and future possibilities? Is time a linear progression, or does it follow a cyclical pattern? These philosophical discussions often venture into metaphysical territory, exploring how time intertwines with existence, consciousness, and the very fabric of reality. Greek philosopher Aristotle. He notably expressed the idea that neither does time exist without change. This thought-provoking statement encourages us to contemplate a world where change is absent. In such a static universe, even the movement of light would cease. The distinction between today, tomorrow, and yesterday would become indistinguishable in this context. Terms such as now, before, and after would lose their significance, leading to a re-evaluation of the very concept of time. This perspective, initially articulated by Aristotle, continues to captivate the minds of contemporary thinkers, prompting us to reflect on the intricate interplay between time and change. Contemporary philosophers have put forward intriguing concepts concerning the nature of time, giving rise to three prominent theories: presentism, possibilism, and eternalism. Presentism posits that only the present moment is real, with the past having ceased to exist and the future yet to materialize. Possibilism suggests that the past and the present exist, while the future remains undecided. On the other hand, eternalism, also known as the block universe, proposes that the past, present, and future all exist simultaneously, with each moment being equally real. These theories, intriguing as they are, lie in the abstract realm of philosophy and metaphysics. What is time? Is it just a concept humans use to measure moments and events, or does it have a concrete existence, like the steady movement of a ticking clock, fundamentally shaping how we perceive the world? Perhaps the answer already exists in the future, tucked away in some corner of the block universe, waiting to unfold. Or maybe time is beyond our comprehension, and its nature will continue to elude us until the end of time. Space is an expansive and enigmatic realm that influences every facet of our existence.
Well, you can't understand anything about the world unless you understand space, because that's the world. The world's space with stuff in it.
We're not usually very conscious of space, but then again, I tell people fish are probably not conscious of water either. They're in it all the time.
Space is not really nothing. It actually has a lot going on inside.
It acts as a canvas for the grand formations of planets, sparkling stars, and vast galaxies, all shaped by the complex interplay of gravity and the hidden fabric of space-time. Even our understanding of time is deeply intertwined with space, as it bends and intertwines in ways we are only beginning to grasp. Despite its omnipresence and significance, space's true nature and fundamental makeup remain tantalizingly out of reach, leaving us with more questions than answers. Before Isaac Newton revolutionized the scientific landscape with his laws of motion, space was often perceived as relational rather than absolute. This metaphysical view suggests that space is fundamentally shaped by the relationships and interactions among objects, rather than being an independent entity. In this light, space is not merely a passive backdrop. It is a dynamic construct that arises from the presence and arrangement of matter. This indicates that the concept of space is intricately linked to matter. In this context, without objects and their connections, space loses its significance and cannot genuinely exist. In the late 1600s, Isaac Newton made groundbreaking contributions that transformed our understanding of space and physics. His work laid the groundwork for classical mechanics and played a pivotal role in advancing the scientific revolution. Newton incorporated the idea of space into his equations by introducing the concepts of absolute space and absolute time. In his landmark work, Philosophiae Naturalis Principia Mathematica, 1687, he proposed the notion of absolute space as a fixed and unchanging framework in which objects move. This idea was essential for his laws of motion and universal gravitation. Newton's first law of motion, commonly known as the law of inertia, states that an object will remain at rest or continue moving in a straight line unless acted upon by an external force. This law relies on the concept of absolute space, as it defines motion relative to a constant reference frame. A well-known thought experiment that illustrates absolute space is Newton's bucket experiment. Here's how it unfolds. Imagine a bucket filled with water hanging from a rope. When the bucket is at rest, the water's surface is level. Next, twist the rope tightly and then release it, causing the bucket to spin. Initially, while the bucket spins, the water remains stationary relative to it, keeping the water's surface flat. As the bucket continues to spin, friction between the bucket and the water eventually causes the water to start spinning as well. This causes the surface of the water to curve upwards along the edges, adopting a concave shape. Even when the bucket stops spinning, the water continues to rotate, and the concave shape remains. Newton argued that the curved surface of the water is not due to the relative motion between the bucket and the water, but as a result of the water's rotation relative to absolute space. This demonstrates the existence of an absolute reference frame, which allows true rotational motion to be measured. Newton argued that the curved surface of the water is not due to the relative motion between the bucket and the water, but as a result of the water's rotation relative to absolute space. This demonstrates the existence of an absolute reference frame, which allows true rotational motion to be measured. The bucket experiment therefore reinforces the idea of absolute space, where motion and forces can be described independently of any specific object or reference point. By integrating the concept of absolute space into his equations, Newton provided a consistent framework for understanding and predicting the motion of objects and the forces acting on them. This notion of absolute space remained a cornerstone of classical mechanics until Einstein's theory of relativity emerged, offering a more dynamic and interconnected perspective on space and time. Albert Einstein's theory of general relativity marked a groundbreaking shift in our understanding of space and time, fundamentally changing the perspectives established by Newtonian mechanics. In Newtonian mechanics, space and time are viewed as absolute and independent entities. Space serves as a fixed, unchanging backdrop, while time flows uniformly across the universe. Einstein's general relativity took this a step further by transforming our understanding of space from a static backdrop into a dynamic, malleable entity. In this framework, space, or more precisely, space-time, interacts with matter and energy, bending and warping in response to their presence. This groundbreaking perspective highlights the interconnectedness of space, time, and gravity, presenting a universe where space is not just a passive arena, but an active participant in the cosmic dance. According to general relativity, gravity is the result of the curvature of space-time caused by mass and energy. Massive objects, such as planets and stars, warp the space-time around them, and other objects move along this curvature, which we perceive as gravitational attraction. While Newton made space something rather than nothing, general relativity made space dynamic and malleable. While general relativity offers a robust mathematical framework for explaining how mass and energy warp spacetime, it does not address the deeper why behind this warping. Essentially, while it describes the behavior and effects of gravitational interactions, it leaves unanswered the fundamental reason why mass and energy cause space-time to curve in the first place. This remains one of the great mysteries in modern physics.
Why is there space rather than no space? Why is space three-dimensional? Why is space big? We have a lot of room to move around in. How come it's not tiny? We have no consensus about these things.
What is space? We actually still don't really know.
It is one of the deepest mysteries in physics.